When you buy a fast food burger, you expect absolute predictability. Whether in New York or Tokyo, you want the exact same arrangement every single time. Delivering that identical experience millions of times a day is incredibly difficult because variation is inherent in every business process. No machine or human operates with absolute mathematical perfection. To manage this, professionals divide imperfection into two camps. There is common variation, the random, inherent background noise of the process itself. Then there is assignable variation, an identifiable factor causing errors that you can track and manage. This chart shows the traditional goalpost view of quality control. The paradigm was simple. Any part falling between the lower and upper specification limits was considered good, costing zero. Once those limits are crossed, the cost of variability jumps straight to high. This chart shows Junichi Taguchi's correction. Taguchi proved that any deviation from the exact dead center target aim costs the business money, represented by this upward curve. To the customer, there is no real difference between a product just inside specifications and one just outside. To stay at the bottom of that cost curve, professionals manage quality across a strict three-phase timeline: design, monitor, and inspect. The design phase happens before the machines are turned on. The primary question here is whether your process is mathematically capable of doing what the customer requires in the first place. This chart shows a normal distribution curve of a process mapped against strict design specifications. Even with the mean perfectly centered, the natural variation of the machine is too wide. The red tails represent the probability of producing defective parts. This is process capability, measured by the Process Capability Index, or CPK. CPK is a ratio showing how well the produced parts fit into the range specified by the design. Here, the orange curve is narrow, meaning variation is low, but the entire mean has shifted off-center, meaning the process is throwing defects. This chart shows an improved, capable process. The standard deviation is reduced, creating a tall, narrow orange curve fitting safely inside the limits. A CPK of 1 or greater indicates a capable process with an extremely low probability of defects. Calculating process capability up front allows a firm to adjust machinery and design out defects long before wasting a cent on manufacturing materials. Once production starts, we enter the monitor phase. The goal now is to keep those machines stable in real time, testing small samples of output to detect exactly when that assignable variation creeps in. Control charts allow operators to visually distinguish between the normal background noise of the factory and special signals that require immediate investigation. This chart maps the 10 visual signatures of a process drifting out of control. Beyond a single point spiking above a limit, operators watch for subtle mathematical warnings, like 5 consecutive points above the central line or a sudden shift. Selecting the right control chart depends on the data type. Variables are characteristics measured with an actual numerical value, like weight or length. Attributes are simple quality characteristics classified as either conforming or not conforming. When measuring variables, you use two charts together. An X-bar chart monitors the average value of your samples, while an R chart, or range chart, monitors the spread or variation within those same samples. Attributes require tracking defect rates. A P-chart tracks the fraction of defective units in a sample, like incorrectly filled claim forms. A C-chart is used when a single item can have multiple defects, like counting the number of knotholes on a piece of lumber. Real-time monitoring turns quality into a stable reality, allowing operators to stop the line before a bad trend becomes a bad batch. Finally, we reach the inspect phase. When a supplier delivers 10,000 parts, checking every unit is economically impossible and often causes handling damage. Instead, companies use acceptance sampling. This is a statistical plan where you test a specific number of units from a lot to determine whether to accept or reject the entire shipment. To set this up, the producer defines the AQL, or acceptable quality level, the maximum acceptable percentage of defectives. The consumer defines the LTPD, or lot tolerance percent defective, which is the boundary where the defect rate becomes unacceptable. This operating characteristic curve maps the probability of accepting a batch against the actual percentage of defective items inside it. This curve visualizes the two inherent risks in any sampling plan. Alpha is the producer's risk, the statistical probability of accidentally rejecting a perfectly good lot. Down at the bottom is beta, the consumer's risk. This is the probability that you accidentally accept a bad lot. Inspection is the final safeguard, a mathematical trade-off balancing the cost of testing against the cost of releasing a failure to the public. Statistical quality control is the quantitative aspect of management. It requires leaders to make high-stakes decisions based on hard data rather than intuition. To secure that quality, you follow the timeline. For potential and design, you measure process capability to ensure your machinery fits the specifications. For real-time stability on the floor, you deploy control charts, catching assignable variation before it ruins the output. And for incoming shipments, you rely on acceptance sampling to balance your risk and keep your supply chain clean. Mastering these 3 phases allows a leader to build operational systems where variation is controlled and defects have no place to hide.